Hi, everybody. Welcome to Richard Blyle's Chemical Principles from Down Under. I'm saying from down under because I am truly under the weather today. I'm sick, but the technical term about how sick I am, doctors would call it Erna dog, because I'm sicker than a dog. But we're going to get through today. Then we have, of course, Thursday off because Thursday is Thanksgiving. And we will pick it up again next week. We are a day behind. We're going to wrap up chapter 9 today, which is not a problem because I really don't think we needed 3 days for nuclear chemistry. So that's no big deal. Even if it were, we still have 2 more special topics days after that. We need to decide if we're going to use those special topics day. You can certainly chime in if you want to send me a message, but I've not heard from anybody since we started this fiasco. Kim, of course, has been with us. Usual participant. Thank you. Welcome, Kim. So I guess it's up to you if we want to do the special topics or not. We're just kind of wrapping up. This is the last day of regular chemistry, so let's go ahead and get to it and see how we do. Today we're basically talking about buffers. Conjugate acids and bases are, we're going to start with conjugate acids and bases. Suppose we have a weak acid, like nitrous acid. Now you have to be really careful with this. Remember, I told you, one of the first things I told you, you change that subscript, you change the compound. We are used to seeing the nitrate polyatomic ion NO3 -1. This is the nitrous polyatomic ion NO2 with a -1 charge. Change that subscript, you change the compound. The nitrous acid is a very weak acid. Nitric acid is very strong. So this is a weak acid. Because it's a weak acid, it does not undergo full dissociation, which means that it is at an equilibrium with hydronium ions. And again, I use H plus. Your book may use H2, H3O plus. One is just as incorrect as the other. The reality is neither of them, both of them, something very different. There's a whole mess of things that can occur. Simplified, we're just going to call it H plus in this class. And the NO2 nitrous polyatomic ion. And of course, the nitrous is nitrate. I like a nitrate because it's always cheaper than day rates. Okay. Now here's the thing. In the forward reaction, HNO2 nitrous acid is acting as an acid. It's giving off a hydronium ion in the Bronsted-Lowry or Arrhenius definition. That's an acid. In the reverse reaction, notice that NO2 minus is acting as a Bronsted-Lowry base. So once an acid dissociates, it gives us what we call a conjugate base. Every acid dissociates to give us a hydronium ion and a conjugate base. Conjugate simply means deriving from the acid. The conjugate base is always written on the reactant side, okay? So this is a conjugate because it's on the reactant side. If we were to write this in the opposite direction, H plus NO2 minus going to HNO2, then it would simply be a base. It would be a Bronson-Lowry base, but it would still just be a base. Because it's on the product side, we call it the conjugate base. Now, I told you this once before. We can always write an equilibrium constant for any of these equilibria. Sorry about that. It's always products over reactants. Every stoichiometric coefficient in this particular reaction is 1. And because we are talking about the equilibrium of an acid, instead of just writing A, we're going to write Ka. That little subscript A represents acid. If we were writing this for a base, this might shock you. We would call it Kb. When we talked about auto-dissociation of water, we called it Kw, but they're all just equilibrium constant expressions. Now, keep in mind that anytime we write an equilibrium constant expression, there are certain things that we leave out because they're basically constant concentration, so they become part of the equilibrium constant. For example, if we put the H2O in here to form H3O plus, you always leave out water. It's kind of an interesting calculation. Turns out the concentration of water in a glass of water is 55.8 moles per liter. You have a concentration just of the pure solvent. And you start adding more things to it, like this Diet Coke. This Diet Coke is mostly water. Turns out the concentration of water in that is 55.8 moles per liter. It doesn't change because all of the other ingredients in there are such a low concentration that they really don't affect the concentration of water in the solvent. So in an acid, we would not write the water, even if we wrote this out as plus, HNO2 plus H2O going to H3O plus NO2 minus 1. So you always leave water out anyway. But if we write out the equilibrium constant concentration, equilibrium constant expression, oops. Oh, wake up, son. Hope you forgive me my mistakes today. Like I say, I am not running on all cylinders. So we get our equilibrium constant expression. Now, you know what? We're going to talk about something else that's very important. LeChateliere. Two biologists got together to do a very simple calculation. Why it took two biologists to do this, I have no idea. The name was Henderson-Hasselbalch. And they did something very simple. It's all algebra. If you're comfortable with how to manipulate logs, remember in algebra, you can do anything you want on one side, provided you do the same thing on the other. Now I'm going to take the negative of both of these, and remember, a log of A times B is equal to the log of A plus the log of B. That's just from algebra. So if I take the negative of both sides, and you'll see why I'm doing that in a moment. And these are base 10 logs, by the way. Now remember, the negative applies to both, so we still have a negative here. Not NO3, son, NO2. If you ever hear me refer to someone named son, that's me. I always call myself in the third person son. Don't ask me why. Maybe it's because I craved somebody to call me son. Well, keep in mind, we should recognize pieces of this. The negative log of the hydronium concentration, that's just pH. The negative log of any number x is px. So here we have not pH, negative log of Ka is called pKa. And we can add this log to the other side. Notice it's the conjugate base over the acid. So we have or rearranging it slightly. And we're going to generalize it as well. Remember, those square brackets represent molarity. This is the Henderson-Hasselbalch equation. Took 2 biologists to figure this out. We just did it in 5 minutes with simple algebra. Okay. It didn't take 2 of them to figure this out. But they kind of studied this. This is a very important equation for buffers. This is a very important equation for buffers. A buffer is any solution that resists changes in pH on addition of an acid or a base. All right? It is any solution, a buffer, any solution that resists changes on addition of an acid or base. This is all based on LeChateliere's principle. And I love LeChateliere's principle. One of the things that I love about LeChateliere's principle is how fun it is to say LeChateliere's principle. LeChateliere's principle states that if we add stress to a system, the system will respond so as to relieve that stress. Okay? If we apply a stress to a system, the system will respond so as to relieve that stress. In equilibria, it means that we can be bullies. We can shift the equilibrium left and right. Going back to our weak acid here, this is the equilibrium we started out with. And we talk about shifting the equilibrium to the left or to the right. So let's add a stress to this system. Suppose we add a little bit of acid from another source. How is that going to affect our equilibrium? Well, if we add an acid, we are increasing the concentration of H+. That concentration is going to go up. Our system doesn't want that to happen. Our system is happy at the pH that it's at. So what it's going to try to do is eat up some of that excess hydronium ion. And how is it going to do that? Well, now this conjugate base, the NO2 minus, is going to kick in. So if we add an acid, the NO2 minus is going to gobble that excess acid up, and it will shift the equilibrium to the left. It will shift the equilibrium to the left. So we add a stress, we add H+. We're adding this, the system wants to get rid of it. So it shifts left, and that hydronium ion comes back down. The pH resists changes because it's a buffer, and this is how. Buffers resist changes. Now, will the pH not change at all? No, the pH is going to change, but only a little bit. pH is not going to change dramatically at all. Suppose we remove hydronium ion. Suppose we add a base, sodium hydroxide. We're going to add a base. We're going to remove some of this hydronium ion. Now the hydronium ion is going to drop. The system doesn't want the pH to change. It does not want that hydronium ion to drop. So it's going to try and generate more hydronium ion. How is it going to generate more hydronium ion to make up for the fact that we removed some? Well, more of our acid is going to dissociate. As this dissociates, we are shifting the equilibrium to the right to form more hydronium ion. Just like that. Now, I'm going to take a real quick caveat here, because this does not just apply to acids and bases. We're going to come back to acids and bases because there's kind of some important equilibria that we should be aware of. But suppose we have nitrous oxide. No. Yeah. It's a gas. Here's a gaseous equilibrium. It's kind of an interesting equilibrium. One of these two, I want to say NO2. I think it's that one. It's very highly colored. It's sort of a brown color. Now, there are some special stressors that we can add to this. First obvious one, we can add one of the components. We can add one of the gases. This is no different than adding a hydronium or removing a hydronium. So if we go from air, for example, equilibrium in air to equilibrium in pure oxygen, then we're going to increase the oxygen concentration. So that's a special stressor. Will this equilibrium shift right or shift left? Well, now the oxygen concentration is going up. System doesn't want the oxygen concentration to go up, so it's going to try and chew up that excess concentration, which means it's going to use more nitrous oxide. To get that oxygen concentration back down, we have to shift right. But what if we add pressure? Now we're not adding a reactant or product. We're just shifting the pressure. We're increasing the pressure. Well, that's a stress. As we increase the pressure, the system is going to want to bring that pressure back down again. How is it going to do that? Well, notice that we have a total of 3 moles on the reactant side and only 2 moles on the product side. So if we're under higher pressure and we remove some gas, that's going to bring the pressure back down. As we remove gas, that pressure is going to drop back down again. And look what happens. If we go from 3 moles to 2 moles, we are removing 1 mole of gas. So how do we bring the pressure back down? We shift the equilibrium right. And that's LeChateliere. Here's a couple of kind of important physiological, kind of important things about this. If you're a scuba diver like I am, I've been diving for decades, so I don't know if I still call myself a scuba diver. But I carry my scuba license. Every time someone says they want a photo ID, but they don't specify a driver's license, I pull out my scuba license. This picture was taken almost 25 years ago now. So it's still a valid license. It has my photo. It just doesn't really look like me. As you dive, one of the dangers of diving is called the bends. The bends is an achiness that usually occurs near your joints, your elbows, your knees, anywhere where your body bends. That's what they're called, the bends. Well, what happens? Every 10 feet that you dive, the pressure on your body goes up by 1 atmosphere. Almost 80% of air, 78% actually, is nitrogen. And some of this nitrogen, not a lot, will dissolve in water. So what happens? As you dive, suppose you're 20 feet, you're at 4 atmospheres of pressure. Because, no, 3 atmospheres of pressure. Increases by 10 atmospheres, 1 atmosphere every 10 feet. I just realized I wrote a blog and I did the wrong thing in the blog. Anyway, need to fix that. You're under 3 atmospheres of pressure. The pressure has gone up. The system is going to respond to try to bring that pressure back down. How can it bring the pressure back down? By getting rid of excess gas. Which means that this equilibrium is going to shift to the right. Because it's trying to bring the pressure back down, it's going to try and get rid of nitrogen. Fewer moles of gas, the less pressure there is. PV equals nRT. The concentration of nitrogen in your blood goes up. When you surface, you're at 1 atmosphere of pressure. Which means that your concentration of nitrogen is too high. What's going to happen? Obviously, we're going to shift left. Now, this concentration is too high. The equilibrium doesn't want that. The equilibrium wants to let some of that nitrogen go. So the equilibrium is going to shift left. Now, if you ascend slowly enough, respiration can take care of this. If you ascend very slowly, respiration will take care of it. So you can get rid of that excess nitrogen through breathing. But if you ascend too quickly, kinetics kicks in. If you ascend too quickly, the nitrogen wants to get out of your blood, and it wants to get out of it now. How does it do that? Well, that nitrogen will form little bubbles. No different than when you open a can of pop, you get little bubbles that form because it's occurring too quickly. That pressure drops too fast. So the gas accumulates in little local spots, in little areas, and forms tiny little bubbles. As a diver, it forms those tiny little bubbles near your joints. You end up feeling sore. It's called the bends. It can be dangerous if it bubbles form in your brain, and some people think they have it. But in order to treat the bends, what do? They put you inside a pressure chamber. To treat the bends, they bring the pressure back up, they redissolve the nitrogen, and then they release the pressure slowly so you can get rid of it naturally. I'm going to write this not quite correctly. So let's not do that. Carbonic acid is in your blood. And it is what we call a polyprotic acid. A polyprotic acid has more than one acidic hydrogen. And it can lose these stepwise, like this. And this is why tap water is not neutral, because there is carbon dioxide in the air. So this occurs in tap water as well, but it also occurs in your body. It is a very important equilibrium because it maintains the pH of our body. But we also have this equilibrium. Now, we've talked about this equilibrium before. Carbon dioxide is very important. Physiologically. And we've talked about hyperventilating before. This is all LeChatelier's principle. When you hyperventilate, if there's one L or two in hyperventilate. Anyway, I'm going to assume it's two. I ain't no English speaking guy. If you're in college, pay attention to those other courses. Pay attention to English. Pay attention to composition. Pay attention for a couple of reasons. First of all, once you graduate, the opportunity for those classes is gone. Good, bad, or indifferent. The opportunity for the experience you're getting, once you graduate, it's just gone. So pay attention, because it's the only chance you'll have for that particular experience. But on top of that, pay attention to grammar, because I don't care how many letters you have after your name, ain't nobody going to take you seriously if you can't talk no good. English matters. Grammar matters. It's how you express to people. When you speak proper English, you're expressing your education level. And people are going to take you more seriously if you speak as if you have, let's say good learning. They're going to take you more seriously if you have a higher education. And the first way that you express your education is by proper use of English, proper use of grammar. So pay attention. It does matter, believe it or not. So when you hyperventilate, you lose carbon dioxide. And as I said, this is all LeChateliere. As you lose carbon dioxide, this third equilibrium is going to try to shift to replace the carbon dioxide, which means that this equilibrium will shift left, eating up the carbonic acid. As you eat up the carbonic acid concentration goes down, which means this first equilibrium will shift left to replace the carbonic acid concentration. And that's when you lose your hydronium ion. Lower concentration of hydronium ion means higher pH. Because remember, it's the inverse relationship there. The higher pH, you get alkalosis, you become too alkaline, you become too basic. And that can be a very dangerous situation. So we've talked about that before. But now here's kind of an interesting thing. Ron Howard, the director, he started off as an actor when he played little Opie Cunningham. Ron Howard directed a movie called Apollo 13. I happen to be old enough to remember Apollo 13. I was too young to understand the details. I was somewhere around 7-ish years old, plus or minus. But I remember in the news every single night. Of course, back then we had nightly news. We didn't have the internet, so it's not like you could go online and see what's going on. No, you waited for the evening news. And every single night in the evening news, something else was going wrong every night. One of the big dangers that they had, and watch the movie Apollo 13 and watch how the engineers solved the problem real time to get the crew back. They did return safely. But Lord, did they have to work at it. One of the problems was that they were in the capsule for too long. The carbon dioxide scrubber, it's a special filter designed to remove carbon dioxide. It's really easy. It's a simple little thing. It's just a filter that has a base in it, something like potassium hydroxide, something like that. And as carbon dioxide goes through, it forms potassium carbonate. So it eats up the carbon dioxide. They weren't supposed to be in the capsule for as long as they were, certainly not all three of them. So one of the big problems was they had too much carbon dioxide. Which means we increased the carbon dioxide concentration. LeChateliere tells us we add a stress to a system, the system will respond to try to remove that stress. That whole problem was one with LeChateliere. The increase in carbon dioxide, LeChateliere says this last equilibrium, this one right here, is going to shift to try to remove that excess carbon dioxide, which means that this is going to shift right. It's going to chew up that carbon dioxide by forming carbonic acid. Well, now we have too much carbonic acid. This equilibrium here is wrong. It's going to shift to the right as well, which means they were not having a problem with alkalosis. They were having a problem with acidosis. Excess carbon dioxide was overproducing acid, too much acid. So when it produced the excess acid, now their pH is dropping. Now they're becoming dangerously low pH. And what happens is your proteins, in order for proteins to work, the proteins have to be what's in what they're called the native state. The proteins are the molecules in the body that do the work. They're the workhorses of the body. And in order for them to work, they must be in the native state, which means they have to be folded correctly. They have to have the right shape. One of my favorite examples is called calbindin. It's a little molecule that binds not one, not two, not three, but 4 calciums. And it does that in order to transport it into cells. It has to bind 4 calciums. And it looks almost like a space station. It has sort of 2 active binding sites connected by a thinner middle tube kind of. If that's not in the right shape, it can't bind the calcium. And if your pH is off, if it's too high or too low, either one, those proteins begin to unfold. You're no longer in the proper shape. And if they're not in the proper shape, we call it denatured. And you're familiar with denaturing. If you've ever fried an egg, you've seen protein denature. They can't work when they're denatured. So if their pH is too low, their proteins denature, they can't do the work, and guess what? They die. The protein in egg whites is called albumin. And it's a very viscous, very thick, viscous liquid. When you fry it, what happens? It goes from that clear liquid to that white solid. That's because the albumin is denaturing. The albumin has a different shape, therefore it cannot maintain its liquid-like structure. And I desperately need a break now because I'm sicker than all. Kim, what do you say we take 5 minutes and we meet back here at 10:40? All right. Recording is paused. We will be back. And we just started recording. Now, you may wonder why it's because I am feeling way under the weather and I don't want to re-record the second half of this lecture. So yes, made sure I read. It's LeChateliere. There's a stress on my system. I'm responding to relieve the stress. It's kind of an interesting way to look at certain things in the world. You don't want to spend time in prison, you pay your taxes. It's LeChateliere. It's pressure on the system. We've been talking about LeChateliere, and we've been talking a little bit about buffers and whatnot. Conjugate acids, conjugate bases. Keep in mind that, well, okay, we'll talk about that. Do you remember what spectator ions are? If they're small, we call them spectator tots. Spectator ions don't really participate in the chemistry, but they're important because they counterbalance charges. So let's look at Diet Coke. Now, the interesting thing about being a chemist is that you can make sense of things when you hear them, but it does not necessarily mean that you would think about it on your own. Coca-Cola products, I read a report at one point that said Coke products decalcify bones. If you drink too many Coke products, my apologies to the Coca-Cola company, because God knows I drink a lot of Diet Coke. But as I'm drinking Diet Coke, my bones are decalcifying. And the reason, according to this article, is because they use phosphoric acid to buffer the solution. And if you don't understand chemistry, people will say, oh, acid, it's going to decalcify bones. Well, no, it's a phosphoric acid buffer, which means it is made, and it goes back to Henderson-Hasselbalch. There you go. Goes back to Henderson-Hasselbalch. It's a buffer, which means that they are choosing the pH that they want. Okay? They're choosing a pH that is safe. It just so happens that the conjugate base and the acid happen to be phosphoric acid. But it's all LeChateliere. Your body has two forms of calcium in the bone. When you're born, the calcium form of calcium in your body is soluble in water, far more soluble than when you're an adult. That, keeping the calcium soluble in water, means it has not calcified the bones yet, which means your bones are flexible because they're not calcified. They're like ligaments almost. Think about like noodles, pasta. It's very flexible. If you and I went through the birth process right now, the stress on our bodies would be so high that we could not survive it. Our bones would just be destroyed by the birthing process. And yet here are these teeny tiny little infants that they go through it, no big deal. Who cares? Well, I mean, I'm sure it's not easy for them, but they go through the birth process. And that's because the bones are still flexible enough that they're squishy. You can add squish to them. As adults, the calcium solidifies in the bones, precipitates in the bones, and forms very brittle, hard bones. By the way, a little bit of trivia for you. The hardest bone known to science is the canine tooth. Dogs' teeth are the hardest bones known in science. That's why dogs can actually eat the teeth of other animals. They're that tough. Anyway, that is a lower phosphate form of the calcium. So when you're born, the soluble calcium is high phosphate. It's a high ratio of phosphate to calcium, and that makes it soluble. As an adult, you have a lower ratio of phosphate to calcium. It goes from three phosphates to two phosphates. And all of a sudden, it's not soluble anymore. And it deposits in bones, and you get calcified bones. So you increase the phosphate concentration, the system will respond to try and bring that concentration back down. How does it do it? It does it by forming that more soluble, lower ratio of phosphate calcium. So what's really happening, it's the phosphate, not the acid. It's the phosphate that is decalcifying the bones. Calcium is going from a lower ratio to a higher ratio of phosphate to get rid of the excess phosphate, and that takes the calcium, makes it soluble, leaches it out of the bones. Phosphoric acid is a polyprotic acid, very strong, so strong, in fact, I'm going to write this as a one-way reaction. But it can continue. Now it's a weak acid. Put the hydronium ion backwards. Let's just, you don't have to change your notes if you don't want to. I'm just wanting to put the hydronium ion first. They're both in there, so it doesn't really matter what order you write them. Making a lot of mistakes today. And I think that's just because I'm under the weather. So there are three. There's not one, not two, but three. Equilibria here. Each one of them plays a role. Physiologically, a physiological pH. Now, by the way, sometimes if you take biochemistry, you'll see something written as PI. PI literally means inorganic. That's what the I stands for. Phosphate. Inorganic phosphate. And it's a recognition of the fact that our phosphate here phosphate in your body actually exists in all four forms. Very small concentration of H3PO4. So inorganic phosphate means that your phosphate in your body exists in all four: H3PO4, H2PO4 minus, HPO4 minus 2, and PO4 minus 3. Inorganic phosphate means that you can have any or all of these phosphate forms in your body at any given moment. You have them right now. At physiological pH, The two major forms of phosphate in your body are H2PO4 minus and HPO4 minus 2. Those are the two forms that your body has most of. Your phosphoric acid starts at a certain concentration, but it dissociates quickly as a strong acid. That concentration drops off. As that concentration drops off, the H2PO4 concentration goes up, but then its concentration will begin to go down as well. As that concentration goes down, HPO4 minus concentration goes up, and of course, an even higher pH concentration goes down, yada, yada, yada. So you have all three, but the two main forms of this one. So, by the way, there are tables of acid dissociation constants. So you can look up, for example, this would be Ka1, this would be Ka2, this would be Ka3. You can look up the values of those Kas. But sometimes you don't find Kas. Sometimes you find tables of pKas instead of Kas. Well, remember, because we know what P means, if we're given pK, that's the same thing as giving us K. We just have to do a little math to convert it back to its regular form. So you can find tables of pKa. In fact, I'm going to look one up here now. So if we look at this, because these are the two because these are the two highest concentration forms of phosphoric acid in physiological pH. We're going to look at Ka2. We're going to look at just that reaction. And it's a good approximation to say, okay, let's just ignore the other forms. There's not much H3PO4, not much PO4 minus 2. It's mostly just those two. So we're just going to assume that is what is in our body. Remember, it's always the conjugate base over the acid. Do you see my phone? Okay, this is really weird because my phone was right here. Did my cat do something? Where's my phone? Ah, there it is. Okay. Let's see if we can find, and I don't know that we can. I am still getting, and this is ticking me off, I'm still getting political ads because of Georgia. I can't, ugh. Someone's at my door.
Someone is at the front door.
Let's see if I can find the pKa for H2PO4. Nice. Okay. 7.2. So for this, for phosphoric acid, the pKa is 7.2. And they are really insistent. I don't know what's going on there. It's ticking me off. Busy. I'm just going to look up here. Okay, physiological pH. Okay, so your physiological pH is somewhere around 7.4. So let's suppose that we want our diet Coke to be 7.4. Okay, that's what we want. So how do we do that? And we're going to make a stock solution. So we're going to start with an H2PO4 concentration of, let's say, 1.5 moles per liter. Well, now we know pH, we want to be 7.4. And we know that the pKa for this particular equilibrium is 7.2. We do not know the concentration of our conjugate base yet. But we do know our acid concentration. We want to be 1.5. Okay? Well, if we subtract 7.2 from both sides, we get 0.2. Take the anti-log. And we get 1.58. Multiply both sides by 1.5. And we see that we need a concentration of HPO4 minus 2 of 2.38 moles per liter, because it's square brackets. So if we have a solution of 1.5 to 2.38, our pH will be exactly 7.4. This is how buffers work. You choose the pH that you want, and you get your ratio of acid to conjugate base, and you're done. This is a stock solution. This is very high concentration, but remember, once we have our stock solution, we can dilute it down to physiological concentrations. So this is fine. This is where we're starting. Okay. 1.5 moles per liter of H2PO4 to 2.38 moles per liter of HPO4 minus 2. That is what this is what the Coke company is doing. They're choosing a safe pH, and they are giving you this mix of acids to conjugate bases to get you just the pH that they want. Now, if I go into my stock room, which I don't have a stock room anymore, I used to have a really well-established stock room. Lots of chemicals. And I want to find some of my acid, H2PO4 minus, and its conjugate base, HPO4 minus 2. Suppose I'm going to find a jar of HPO4 minus 2. No, of course not. Oh, shit, that was a cop. Okay. The police are doing something outside. Should be kind of interesting. I may have to go and see what they're doing. So here's the catch. You cannot, remember, the world is electrically neutral. You cannot have a jar of free-floating ions, and they just don't exist. So I'm not going to find a jar of HPO4 minus 2 because you can't have that charge ratio. But what I do have I might have, for example, instead of H2PO4 minus, I might have potassium phosphate. Well, guess what? In water, this is an ionic compound. So in water, this is going to dissociate. Why did I write that so large? Clunky. This is going to dissociate. So whenever we see ions like this, we have to find something that has the ion in it. This potassium will be in the solution as well, but it's a spectator ion. The spectator ion doesn't really participate in the reaction. As a result, sorry, I'm distracted now because the cops outside. I should go see what they want. Anyway, because of the spectator ion, it's not going to participate, but it has to be there because I don't have a jar of H2PO4 minus. Maybe for HPO4, I have this. Now the calcium is a spectator ion. So I might have a solution of these two salts, which means I have both potassium and calcium. Remember, calcium is +2. So that +2 would cancel the -2 charge on HPO4 -2. Notice in a balanced equation, it's not just mass balance, it's also charge balanced. So we're going to have to find a salt that will dissociate to give us the charged species that we want. And those salts will have cations that are simply, spectator ions. Kim, do you have any questions? All right. I'm going to call this. We're going to call it about 10 minutes early today because the cops are outside. They probably want to come to arrest me. I'm kidding. I can see them through my window. I don't know what's going on, but must be kind of a serious crime because usually when they come to my door, it's because they want my Ring video, security video. I don't think I did anything worth being arrested for. Oh, shit, maybe I did. Oh, I said shit. Sorry. If that offends you, please feel free to contact me. I will give you a full refund on your money. But Kim, this pretty much wraps up the chemistry, the regular chemistry. We're going to do nuclear chemistry next week. We're going to spend just a couple days on that. And then we have, are you thinking about special topics?
I'll give it some thought.
All right. So we can talk about special topics next week, week after next, if you want. Meanwhile, I hope you have a terrific Thanksgiving. Thank you for participating, and I am out of here.